Great. So recall, we wanted to show, so we had this theorem, Z is a principal ideal domain, i.e. every ideal in Z, if we were calling this S, so S is an ideal, well, we can start with a finitely generated ideal, and then we'll talk about what happens in general. So this is an ideal. The ideal generated by elements n1, integers n1 through nk, what does that mean? Devendra. Yeah, integer linear combinations. So it's just the set of all n1, x1 plus nk, xk with xj in the integers. Is this amount of abstraction okay? Everybody understands what this means? I give you integers n1 through nk, 5, 17, 24. You form all linear combinations, an integer times 5 plus an integer times 17 plus an integer times 24, and look at all the integers that arise in this way. Okay? So that's what this ideal is. And the theorem is, so if S is an ideal, then there exists an integer D such that S is actually the ideal generated by D. And it's easy to see what that integer D is. It's the GCD. Okay? Is that better or worse?
A little bit brighter.
Better?
Yeah.
Okay. All right. Let's start with just an ideal generated by two elements, and then we can recurse from two elements to a finite number of elements to an arbitrary. Well, there's only countably many integers, so we only need to think about countably generated ideals. But so we started with the proof. Start with the ideal generated by n and m. So if we have, let me put one more, x2, dot, dot, dot. So if we just understand what happens to the first two linear combinations, if that can be recovered by some integer, then we can look at integer multiples of that integer times the next one and so on. So we can recurse out from what happens with two. So what happens with two integers? So this is the set of all things of the form nx plus my. So I don't have to use subscripts. And we sort of rushed this proof, so let's go over it a little bit more slowly. So we want two directions. We want to show, first of all, that any linear combination of n and m is divisible by the GCD. So fact one, or one direction, fact one is if something divides n and it divides m, then it divides any integer linear multiple, any integer linear combination of n and m, which means the GCD of n and m will always divide nx plus my. Okay, so what does that mean? That means that anything that's of the form nx plus my is also a multiple of the GCD. So S is contained inside any multiple of the GCD. In other words, it's contained inside the ideal generated by just multiples of the GCD. Does that make sense? The GCD of n and m always divides nx plus my. So anything that's of the form nx plus my is a multiple of the GCD. Now we want the reverse inclusion. Back to. Well, our claim is that the GCD is in S. So the claim in the other direction is that the GCD of n and m is in S. Which would imply, well, if S is contained in here, but the GCD is contained in S, then we have an exact equality. So it might be that S isn't just the multiples of the GCD, but it's only the square multiples of the GCD. Or no, that's bad because 1 is a square. It's only the even multiples of the GCD. How do I know that the GCD itself is in S? Because it's an ideal, so if the GCD is in here, then this is an actual equality. So that would imply that the ideal generated by the GCD contains an S, which implies this is actually an equality. Which implies that S is a principal ideal. Does that make sense? This is not too abstract for you guys? Tell me, okay, Karen, can I ask you to raise your hand?
Well, I have a question.
Oh, awesome, even better.
So S can only be the principal ideal?
Yes.
Okay.
Yes, that's the crazy thing. No matter what linear combination of numbers you start with, any set of numbers you choose, n and m, give me any n and m, and look at the set of all linear combinations of n and m, that will always be just the set of all multiples of a single integer.
So there is misleading where we have n1 with n and we only need one n?
I don't know if misleading is the word I would use, but this is a starting point that if we start with two numbers, so this is the case of k equals 2. First, we're proving this theorem in the case of k equals 2. So any pair n1 and n2, if you look at the linear combinations of n1 and n2, that's the same as some integer d1 times some other number y1. But then if we want to look at larger linear combinations, we can just do it a pair at a time. And any combination of this is some combination of the first two and the third and the fourth and the fifth and so on, and the kth. And so if we do it 2 at a time, each time using this GCD algorithm, we fill out the entire set S and we realize it as the multiple of a single integer. Okay? Does that make sense? Now who's lost? Thank you, Kevin. Where are you lost? Back me up.
Just like, could you like explain like
Yes. Let's do an example. Let's do another example. We did some examples last time, but maybe that was 4 days ago or something, and long enough ago that we needed more examples in our mind. So Kevin, give me some integers.
5 and 17.
Okay, fine. 5 and 17. You want to give me any more?
26.
26. Okay, so my claim is that there's a single integer, so that the set of all linear combinations, integer linear combinations, my claim is that there exists a single integer, d, such that the set of all linear we're going to have problems here. The set of all linear combinations of, well, 5x1 plus 17x2 plus 26x3 as the xj range in the integers. Can you see that? I'm having ink issues. The set of all combinations of this is the same as the set of all multiples of a single integer, d times y. as y ranges in the integers. How many of you know what d is already, without shouting it out? Okay. So Kevin, can I continue picking on you? Do you mind?
Yeah.
Okay. So give me some elements. So this is our set S. S is this ideal generated by 5, 17, and 26. So what are some elements in here? Who do you know in here? How about if all the x's are 0? 0's in there. How about 1, 0, 0? 5 is in there. 17's in there. 26 is in there. How about 5 plus 17? 20, yeah, 22. Sounds good. Who else is in there? 43 is in there. Let's start with some negative values. How about a 17 but negative 3 5s? That'll get us 2. So 2 is in there because 2 is equal to negative 3 times 5 plus 17. But notice that once we have 2 in there, we also have all even numbers in there. Because you just multiply this equation by your favorite integer k, and 2k will be negative 3k times 5 plus k times 17. So all evens are automatic. Once 2 is there, all evens are automatically in the ideal. So all evens are there. 2k, it will be equal to negative 3k times 5 plus k times 17. So every even number is an S. Can we do better than just all the evens? What's that? Maybe prime numbers. We can even do better than prime numbers. Once 2 is there and 5 is there, what is 2 of these minus 1 of these minus 2 of these? 1. Right? Notice that 1 is equal to 5 minus 2 2's. But 2 2's, we know what 2 2's are. So this is 5 minus negative 3 times 5 plus 17 times 2. And if we write this out, this is a linear combination of 5 and 17. I just wrote 2 as this. And then, so what does this come out to? Negative 6 plus 1 is 7 5's. So this is 7 times 5, I guess minus 2 times 17. So the combination of 7 5's, which is 35, minus 2 17's, or plus negative 2 17's, which is 34, 35 minus 34, gets you 1. And once 1 is there, every multiple of 1 is there. And so that integer is 1. And the ideal generated by 1, so d equals 1, d equals 1, and the ideal generated by 1 is all integers. So in this case, because these three numbers, 5, 17, and 26, were coprime, their GCD is 1, and you get every single integer in their linear combinations. We didn't even bother using 26, by the way.
But you can use different combinations.
We could use
17
different.
and
Yep.
26.
Yep. The question isn't how many ways can you get 1. Well, you can already get 1 infinitely many ways from just the first 2 already. But you can also get 1 from 26's and 17's, or you can get 1 from 5 5's, 26 minus 5 5's. There's lots of different ways of getting 1. The question isn't the multiplicity, it's which integers will we see, period. Now, if instead of 17, so that was one example. This is good. I'm glad you asked this question because I think other people are also getting a little lost in all of the algebra and abstractness. Let's do one more example that I think will. So now give me 3 numbers that have a GCD. 5, 10, and 15. So S is equal to 5x plus 10 x1, x2 plus 15 x3. As the x's range, you get any multiples of 5 any multiples of 10, but of course all multiples of 10 are already multiples of 5. And you get any multiples of 15, but of course those are also all multiples of 5. So this is just all multiples of 5. So this is equal to the ideal generated by 5. And 5 is there. Now 5 is one of the entries, so it's a little bit cheating. But if we had just taken 35, 10, and 15, now it's a little bit more interesting because we have to find 5. How is 5 a combination of these? Well, it's one of these minus one of these. So 5 is the GCD. We can find 5, and we can't find more than multiples of 5. So that's what this proof is. The proof is, first of all, anything will be a multiple of 5, because 5 is the GCD. So any element in S, any linear combination of your n and m, is going to be a multiple of the GCD. So this is this containment. The opposite containment is, can we actually find the GCD inside the multiples? If we can, then any multiple of the GCD is also one of the multiples. And hence, we have an exact equality. We've completely identified what the ideal generated by n and m is. It's just the ideal generated by the singleton of the GCD. Does that make sense? And so that's the claim. This fact 2, the claim in the other direction, is we can find the GCD. How do we find the GCD as a linear combination? Benjo? Euclid's algorithm. Euclidean algorithm. Exactly. Okay? So we know how to do this. So in other words, we want x and y, or x1 and x2, x and y, such that nx plus my is equal to the GCD, let's call it D, GCD of n and m. Can you see that? It's starting to get a little small. And we know how to find that algorithmically by the Euclidean algorithm. But we can prove abstractly that we will find it. And the proof, so proof of claim, this is fact 2. So let's go back to fact 2. Proof of fact 2, or claim 2. Look at the set of integers that are in S. Look in S. And find, let's call it R in S, which is the least strictly positive number. Strictly positive element. Okay? So R is some combination of n and m. R is some combination of n and m, which means, how did we finish this last time? You guys remember?
Do we have to use the algorithm?
Sorry?
Do we have to use the Euclidean algorithm?
Right. So we can run the, yeah. So we can run, we know that the GCD, we know that D, how do I want to say this? We know that, well, yeah, without writing out the Euclidean algorithm again, what I want to say is that R must be equal to D. So the GCD, Euclidean algorithm, let's write it like this. Euclidean algorithm implies there exists a solution to nx plus my equals the GCD. Can you still read this? Is this getting too small? I'm having nx plus my equals d. So y is the smallest element, also d, the smallest positive element.
Is it smaller than R? Is D smaller than R?
My claim is that d is equal to r.
Oh.
And the claim is that this smallest element is actually the GCD. And that's because you can't get any smaller because D is a multiple of, N is a multiple of D, and M is a multiple of D, and this is some linear combination. I'm making this more complicated than it needs to be. I mean, we already proved that direction, since D divides N and D divides M, which implies that D divides NX plus MY. So basically, this part will tell you that anything that's integer linear multiple of N and M has the GCD as a factor, and we know we can solve this equation by the Euclidean algorithm. We proved last time that the Euclidean algorithm exactly captures the GCD. And so for any two integers, you can represent D, and you can't represent anything other than multiples of D because you're stuck inside the world of multiples of D. So that's it. That's for pairs of numbers. Once we have pairs, so once we know that the ideal generated by N1 and N1 and N2, say, is the ideal generated by D1, what happens to the ideal generated by N1, N2, and N3? So again, this is integer linear multiples of N1, N2, and N3, linear combinations. But I know what all the linear combinations of these two comes out to. It comes out to
N1 x1 plus N2 x2 plus
yes, anything that's of the form N1 x1 plus N2 x2 is just of the form D1 y. So this is the ideal generated by D1 and N3. And now we apply the previous argument, and that gives us an even further GCD. Where D2 is the, so D1 is the GCD of the first two, D2 is the GCD of the first two and the third, which is the GCD of all three, and so on. Okay, and so on. Does that make sense? Okay. Charles.
You said D2 is the GCD of all three N1, N2, and N3.
Yes. So D1 is the GCD of just N1 and N2, and D2 is the GCD of D1 and N3. Let's try that again. D1 is the GCD of N1 and N2, and D2 is the GCD of D1 and N3. And actually, I'm supposed to be giving you exercises, and I keep forgetting, so let's make this an exercise. D2 is the GCD of N1 and N2 and N3. So the GCD of two numbers and a third number is just the GCD of all three numbers. It's not a hard exercise, but it takes a little thought. Okay? Don't tell me Joseph.
Yeah. So, in our proof, R is the least element in S.
Yes,
And then our claim is that R, and this is for pairs.
that's right.
And then we claim R is equal to D.
Yes.
But that's not always true.
Why not?
Well, if you have, if S is 4 and 6,
Yes.
GCD is 2,
Yes.
and 4 is not 2.
But 6 minus 4.
Yeah, but our claim is R equals D.
R is the least element in S, not among the integers N1 through N2. S is the all linear combinations.
Okay, that's it.
Yeah, great question. Great question. Thank you for clarifying. Okay, so S is all linear combinations, and that's why it's not just R isn't one of the either N or M. It's the smallest linear combination that we can get out of them. We have 4 and 6, so we can make 6 minus 4. So we'll make 2, and 2 is the smallest that we can get because 2 divides both 4 and 6, so we can't get anything that's not even. And we can find 2, therefore we get all multiples of 2. So all even numbers will be generated by that idea. All right, maybe this seems like silly and we came up with all this fancy language, ideals and rings and principal ideal domain and so on. And what is it really useful for? Because at the end of the day, these are just whole numbers and we know all the properties of whole numbers, right? I mean, what we're headed towards is a proof of the fundamental theorem of arithmetic. So let's just very quickly finish that if we have time. I think we do. Let's very quickly finish the fundamental theorem of arithmetic. Karen? Ooh. Wow. Let me try it. Thanks. I'll give it back to you. Remind me if I forget. Yeah, these are better, right? These are 2. Let's see if this works. Wow. Okay, I'm going to the store after. Thanks, Karen. Right, so we have proved the theorem that the integers as a ring are a principal ideal domain, because any ideal, we can start with finitely generated ideals, but any ideal is just, any ideal, it can be realized as an ideal generated by a single element, and that's what it means to be a principal ideal. Blank stares. Sheep.
Can I ask you a very basic question?
Please.
What is an ideal? What does it mean?
Okay, so this is what we, let's recall. An ideal, so a set in a ring, S in a ring, R, a ring, is an ideal, is called an ideal if, again, this is like, you have to blame Emmy Noether for introducing this kind of, this way of thinking about things. Actually, she completely revolutionized our understanding of algebra through largely introducing these kinds of abstract ideas, as you'll see in a minute. There's an old-fashioned notion of an ideal number, and it's the right kind of number to deal with the fact that there are units in other number fields. Never mind, that's not going to mean anything. What it means, the formal definition is something like, if I have 2 elements, Z1 and Z2 in S, then their sum and their difference, Z1 plus or minus Z2, will also be in S. And any integer multiple, or in general if you're in a ring, any multiple from the ring of an element of the ideal is also in the ideal. Okay? So that's why things of this form are exactly the things that form an ideal in the integers.
What do you mean by like N1 through N something like that?
So the notation N1 through Nk means generate an ideal from the numbers N1 through Nk. What that means is I need to be able to multiply by an arbitrary integer, and I need to be able to add and subtract. Well, add, because the negatives are in the integers anyway. So that means any integer linear combination. So I give you numbers, and I say make the ideal generated by them. That means take the integer linear combination.
Okay. And if it's
Right. If all you did was took one number and took its multiples, that's a principal ideal. So, as you said, you start with something generated by k elements. That is the same as something generated by a single element. So every ideal, arbitrary, is actually principal. It's just generated by a single element. Charles.
So, let's say for example, we have an ideal of rank 2, so like n1, n2.
Yes.
We can multiply, so like let's say 2 n1 will also be in the ideal, right? Or
Yes,
times
yes.
n1.
2 times n1 will also be in the
About
ideal.
n2 minus 2 times n1.
Let me write down what you're saying. So, if we have an ideal and it's generated by n1 and n2, then 2 times n1 is in the ideal. I agree completely. As is
2 times n1 minus n2.
I agree completely.
Okay, so basically, it's just the combination of anything inside S.
Yes.
Okay.
It's just so this is literally all of the integer linear combinations. So when I'm writing this, what I mean is take x1 equal to 2 and x2 equal to 0. Or take x1 equal to 2 and x2 equal to -1. or take x1 equal to 7 and x2 equal to 0. Or, right? So as x1 and x2, this is as x1 and x2 range over all integers. That's exactly what it means to take the ideal generated by these two numbers. I should have reviewed this. We went over this last time, but that was many days ago, and we had just introduced this new notation. I should have reviewed it. So that means that everything I said all back here didn't make any sense because we were still confused about what it means to be this ideal. So should I go over this one more time? Quickly? Yes?
Yes.
Kevin, question?
What would be an example of an ideal rank 2?
Well, an ideal, what this theorem says is that any ideal of rank 2 is really an ideal of rank 1 in the integers. So an ideal of, you can say, well, depends on what your definition of rank. For some people, you just give me some number of elements, and that's the rank. So this is an ideal of rank k. For some people, rank means the minimal rank, and in which case, what this theorem says is the rank of any ideal in the integers is 1.
So any ideal of the integers
Is always principal.
principal.
Principal. Yep, that's the theorem. Joe.
Isn't closure under addition and subtraction and scalar multiplication axioms of rings? So if a ring is not ideal, doesn't that imply that it's not a ring?
The ring itself is also an ideal in itself. So Z is an ideal in Z. For exactly that reason. So the ring will always be an ideal in itself. The ideal generated by 0 will always be an ideal. But it just contains 0 and nothing else. Any integer multiple of 0 is 0, and any linear combination of 0 is 0. So the element 0 is always an ideal. The element R, the set R, the entire set itself, is always an ideal. Yes? Is that a question, Daniel? No. Other questions? This stuff I think will make more sense when we move. I want to finish this discussion and get to the fundamental theorem of arithmetic, and then move to another ring where all of this stuff becomes non-trivial, where now you really are scratching your head and you're realizing why these definitions were made. Kevin?
Do you have like ideas of complex numbers?
Yes, that is literally where we're going next.
Oh.
Fine, forget the fundamental theorem of arithmetic. We'll come back to it. You guys are interested in this, let's talk about this. Fine, let's change our ring. Let's really get a feeling for what is going on here before we get to the fundamental theorem of arithmetic. Now, try R is equal to the Gaussian integers. These are called the Gaussian integers. I give up. You guys want to talk about rings? Let's talk about rings. Exercise. This is, what does this mean? Z adjoin I. What does that mean?
Set of complex numbers?
It's a set of complex numbers whose coordinates are integers. So x plus iy, where x and y are integers. So who's in here? 7 plus 3i. Negative 2 plus 17i. These are typical elements of the Gaussian integers. Exercise. This is exercise 1. This is exercise 2. This is a ring. i.e., what do we need to show that to see that it's a ring? The sum of two z1, z2 in this ring implies z1 plus z2 is in the ring. And this is the one that takes a little bit of, this is not hard. You just do it coordinate by coordinate. And z1 times z2 is in the ring. So let's think about this for a second. What is, example, what is 7 plus 3i times negative 2 plus 17i? Aren't we going to get something weird? Are we going to get something of the form an integer plus I times an integer? Yes. Okay, take 10 seconds and just compute this and tell me what you get. Give me a hand when you've expressed this as an integer plus I times an integer. Okay, I'll do it 2, negative 14, minus 6i. Oh God, 7 times 17, 70, 49, 119 plus 119i. That sounds right. And now what? 3 times 17 is 51. I squared is minus 1, so this is minus 51. Okay, that's the magic. That's the thing that makes this a ring. If I told you, well, how about linear polynomials? Do linear polynomials form a ring? Okay, exercise 3. Well, let's fix this. Let's finish this example. So negative 14 minus 51, negative 56, 66, 65. I'm dyslexic. 10 and 50 is 60, and 4 and 1 is 5. Okay, and then 19 minus 6. Plus 113i. Okay, and that's an integer plus I times an integer. Okay, so that's an example of this exercise. Exercise 3. Exercise 3 to do at home. Let R equal linear polynomials over the integers, i.e. an element of R in R, I keep writing the real numbers, I don't mean the real numbers, in the ring R, if R is equal to an integer plus m times a free variable x. Okay, this is a linear polynomial in the integers. Is R a ring? Well, it's an exercise, but all right, Charles, you want to ask a question?
Just a question. We just show that under addition and multiplication, it comes out to be the form n plus m x, right?
Yep. Sorry, you're asking about the
Exercise 3.
Exercise 3. Yes. If I
It's
add,
be of that form after multiplication.
yes. Will it be? Because? Yeah, product of linear polynomials is quadratic. Okay, so this is not a ring. I gave away the exercise, but do it anyway. It's not a ring. What is amazing is that when we see I squared, we get to turn it into an integer, negative 1. Karen.
Can you have like a ring with a square root, so it's an integer plus an integer times a square root?
Yes.
Okay.
Exercise. Great question. Exercise 4. Exercise 4. Let R equal z adjoin root minus 6. So this is the set of all integers x plus square root of minus 6 times y, where x and y are integers. Is this a ring? Does anybody know if this is a ring? Yeah, it has an I in it. It has a root 6 I in it. Alex?
Well, you multiply the two y's.
Yes.
This, you would get -6, but you would get a root when you did y times x.
Yes.
So it would still be the same form.
Yes. I'm not going to give away more than that. It's an exercise. Alex gave away the exercise. Okay? The point is, you do it. You do it. Think about it. Do it at home. So this is not a ring. This is a ring. If this ring, now I'm really getting ahead of myself, is this ring a principal ideal domain?
It's generated by one element, yeah.
So the fact that I'm trying to work up to, fact, is if your ring, if R is a principal ideal domain, then it has unique factorization. Then it's a unique factorization domain. This is unique factorization. You have to make sense of what that means. In other words, the fundamental theorem of arithmetic holds in that ring. And here's something really weird. Oh, I put the wrong number here. Make that a 5 instead of a 6. I need a 6 in a second. This ring is the simplest, in a sense, ring, which is not a principal ideal domain. Okay? Yes, because you can factor, because observe that 6, which on one hand is 2 times 3, is also, Devendra? Do you know what? You know how else you could factor 6?
Okay, 1 minus something. Okay. Is that with the golden ratio thing?
The golden ratio is with a plus here instead of a minus. This is imaginary quadratic field. Golden ratio is a real quadratic field. I'm getting way ahead of myself, but it's too much fun not to just plant some seeds into your head about the fact that we're starting to touch serious issues. This is a number field with class number greater than 1. We'll get to what all of that means in a second. Can we go back to the Gaussian integers, which is the world that, so back to R equals Z adjoin I, the Gaussian integers. Do we have a division algorithm? The thing that made everything go, if you remember, in the integers was the Euclidean algorithm. And the Euclidean algorithm we got because we had a division algorithm. So what we want, do we have a division, a nice division algorithm? In other words, i.e., can we write n as m times q plus r with r simpler than m? So now we're talking, now these are not integers anymore. These are Gaussian integers. Given a Gaussian integer n and a Gaussian integer m, can I find Gaussian integers q and r, where r, well, what did we do last time? We said r was strictly less than m when we were dealing with integers. And now we need some other notion of simplicity, Devendra.
You're not forcing Q and R to be unique.
I'm not forcing,
Q and R to be unique. Like, you know,
I don't insist that they're unique, and in fact they won't, even in the integers, well, they're unique because we'll insist on r being positive. But now, there's no notion of positive. There's no good notion of positive. Kevin.
Can you like take like the Euclidean distance rule, like so like square root of like whatever the real component is squared plus the imaginary component squared?
Awesome. Awesome. So Kevin's suggestion, so Kevin's norm. Norm is a way of measuring complexity. How complex is this number? is to take, so let's call this n of x plus iy to be
Oh, like square root of the open square.
Yep. And we can even, because we just care about the complexity, you could put a square root here or you could not put a square root. It actually ends up being better in this case if we don't put the square root. So just to put x squared plus y squared. By the way, do you guys remember how we got to this nonsense? We were trying to figure out what numbers are.
Oh, trying.
We were trying to figure out what numbers are sums of two squares.
Yeah.
So sums of two squares is a norm form. Okay, again, I'm getting ahead of myself. So Kevin's suggestion is, let's try this as a measure of complexity. So here's the exercise. Now this is real. We're not messing around anymore. We're in grown-up world. 4. Example. We had some nice numbers here. How about n is equal to -2 plus 17i, and m is equal to 7 plus 3i. First of all, which one's bigger?
And
17 squared plus 4. I don't have to do that much computation in my head to guess that that's not going to be smaller than 49 plus 9. Okay, so n is the bigger one. So find q and r as Gaussian integers so that the norm of r, it might be positive, it might be, well, it might be 0. It might be 0. But all I want is that it's strictly less than the norm of m. And the norm of m, just to get it on paper, 49 plus 9, 58. Does everyone understand the challenge? Alex?
Can you just explain what norm is again?
The norm of a Gaussian integer is just the sum of the squares of the components. So the norm of m is 49 plus 9. It's also, by the way, the product of the integer itself, the Gaussian integer itself, with its conjugate. Let me plant that seed in your head. Okay, Charles.
Is there a reason we chose x squared plus y squared?
There is, but there'll be other rings where we want to choose different numbers for norms. And this will be the hint for the right way to choose what the norm should be. But we're going to come back to that.
Is
You
Q
comment.
and R unique?
Are Q and R unique? Well, very good question. Play with it. Play with it. See if you can find more than one. So there's an issue here. There's an issue which is that we have lots more units now. Remember what a unit is? We discussed units. Like the units mod n are the numbers for which there is another number, so that when you multiply the two, you get 1. They're divisors of 1. So in the integers, the divisors of 1 are 1 and -1. They're the only numbers that have somebody that you can multiply by. Who are the units here? 1 and -1, and I and -I. Okay? So that really is going to, I didn't say this was unique, but it will still lead to a Euclidean algorithm. Because if the norm is always getting strictly smaller until you hit 0, at some point you hit 0, and then that's what we can say is a GCD. There's no such thing as GCD, because GCD, there's a greatest common divisor. There's no way to measure who's bigger when you have complex numbers. Actually, that's another good exercise, but maybe, let me not do that one on you now. Okay, does everyone understand the challenge? Find numbers, find Gaussian integers, Q and R, so that m times Q plus R gets you n, and the norm of R is strictly less than 58. Take 5 minutes, see if you can figure out how to do this. This is really challenging, so if you're totally stuck, give me a, raise your hand and talk to your neighbor and so on.
If I change R as the smallest norm, it can be infinite.
Even among numbers of the same norm, there's R, IR, negative R, and negative IR. So even numbers with the same norm, not to mention that if I change x and y, well, that's multiplication by I anyway. Or the conjugate has the same norm also. So that's what I mean by there's an issue with uniqueness. But just find me one. I'll be happy with one. Shane? Ray? Is anybody making progress, or is everybody totally stuck? You got it? Talk to your neighbors. Discuss. If you're stuck. Even if you're not stuck, help your neighbors. What are you guys doing? Trial and error? Are you, what are you trying? Trial and error? What would you do in the integers? Let me give you a hint. What would you do in the integers if I gave you some large number? What are you doing? If I give you, 171 is equal to 27q plus r. How are you finding q? Joe. No, sorry, Joe. Drew.
Yes. You're trying to find Q as you're trying to get 27 as close to 171 as possible, but less
Yes,
than
it's the quotient.
Yeah.
So we would just look at the number 171 over 27 and find the nearest integer to that. Q is the integer part. The integer part is Q. Q is the quotient, R is the remainder. Does that make sense? Charles?
How do you divide n and m?
Yes, that's exactly the question. Yes, that's the question. How do you divide n and m? Awesome. That's the issue. How do you divide n and m? Right? Do you guys want to think about it, or should I give you a hint? Will?
So just how do you divide n and m?
Yeah.
Can you just put it in a phasor form?
Put it in.
Phasor?
Phasor.
Change the form of it and you deal with the bottom?
The answer is yes, except I don't know what that word means. But
I just said the wrong word. N would then be equal to the square root of 2 squared plus 17 squared. Cosine of something.
Oh, you want to put it into polar coordinates.
Polar coordinates, yeah.
Gotcha. You can do that. You can do that, and that's more computationally intense because now I have cosine of 2, arc cos of 2 over 17, or arc tan or something of 2 over 17, and I want to multiply that by another arc tan. There's a way that avoids transcendental numbers, but this is exactly the issue. What is this ratio? How do you figure out what the hell this thing is? And then you have to think back to school, Kevin.
Multiply the
Conjugate.
Yes, if you remember in school, they stuffed this down your throats that this isn't the answer because you didn't give it to me in a nice form. And then you have to oh God, I have to multiply by the conjugate or something to make it nice. Yes, the reason they stuffed that, I don't think they knew why they stuffed it down your throat. Now, the reason is so that you would be here today. That's why they stuffed it down your throat. So that you would know to multiply by the conjugate. So I would multiply top and bottom by 7 minus 3i. Because what that accomplishes in the denominator is
It's gonna be 58.
58, exactly the norm. And 58 is a rational number, which means I can multiply it by both the imaginary part, or 1 over 58 I can multiply both into the real part and the imaginary part. Cool?
Yeah.
Now keep going. That's the hint.
Okay.
The hint is look at the ratio, find a nearby integer. Yukong, will that nearby integer be unique? If I have, here's the complex plane, and here are the Gaussian integers, C adjoin I, and then I have some value here, is there unique closest value to it? Well, maybe there is a closest. Maybe it's right in the middle, and then there's really no good choice. But it actually doesn't matter, because whichever one you take will have a remainder that's smaller than what you divided by. So there is an issue with uniqueness. So now give me a hand when you figured out what Q should be and hence what R should be.
Is that fraction under the float function equal to Q, or is it a question mark?
No, what I'm saying is, how would you find Q here? You would take 171 over 28 over 27.
But why just that number?
Well, so what are we doing here? We're finding the quotient and the remainder. The quotient is, take this ratio, you don't get an integer, but what's the integer part? That's the quotient. What's left over? The remainder.
Yeah.
That's exactly what we want to do here. You take n over m, you have to figure out how are you dividing by a Gaussian integer. Can't divide by a linear polynomial. Can divide by a Gaussian integer because when you multiply by the conjugate, the norm is always a rational number, in fact an integer. And so now we can make a rational Gaussian rational number, not a Gaussian integer. And then we can find a nearby Gaussian integer, and that is what we should call Q. Alex.
This might be a stupid question, but can x be 0?
Sure. Yeah. Sorry, I didn't put dots here. These are all Gaussian integers. Not a stupid question. It can be negative. Okay. These are the Gaussian integers sitting inside the complex plane. Who has now finished the computation? All right, let's do it together. Karen, can I pick on you? What did you get for this product? I get a
Negative 44.
okay, negative 14 and a negative positive 51. 51 minus 14.
Just putting positive.
Positive 50?
44.
Positive. What is it?
44.
51 minus 14.
51 minus 14. Oh, never mind.
Did anyone do this? You're going to rely on me? Come on, we can do this. This is a negative and an I squared, so that's a positive. 3 times 17 is 51. 51 minus 14, 37. Okay, does that sound right? 37 And then what's the I part? Plus
124.
Yeah, so we're going to get a plus 6 and a plus 1. We did this already. 17 times 7, 119. 119 plus 6.
125.
119 plus 6, 125. So what is a nearby integer to this? We have 37 58ths, that's here. And 125 58ths, that's about 2. 58 times 2 is less than 60 times 2, which would be 120. So we're here-ish. And so what's a nearby rational number, nearby integer? Maybe 2i? So that is what we might guess to be q. Charles?
Can you explain how you got 2 again?
Yeah, I'm just looking at these. I'm just looking at where this rational number is. So this is in Q adjoint I. This is no longer in. This is no longer in the Gaussian integers. It's a Gaussian rational, just like 171/27 is a rational number. And now I want to find a nearby integer. So by the same token, I'll take this number, which is this is like between 0 and 1. And this is 125 58ths, which is going to be like a little bit more than 2 and change. So that's like between 0 and 1 in the x variable, and then between 2 and 3 in the y variable, so it's somewhere here. And then I chose the nearby, who's nearby this point, that's a Gaussian integer. How about 2i?
Where does the I come from?
Oh, where does this I come from?
No, the 2I.
The 2i. So it's that this ratio, so once I have an over 58, that means just 37 58ths plus I times 125 58ths.
So it's like 2I plus 0, right?
Exactly. This is like 0 and this is like 2.
Oh, okay.
So this is like 0 plus 2i. So I'm going to make q equal to 2i. Let's see what happens. So if q is 2i, remember what we're trying to do. We want n is equal to mq plus r. In other words, r is equal to n minus mq. And now we have to do a little computation. N is negative 2 plus 17i minus m times q. M is 7 minus 3i. Q is 2i. Should I give you 10 seconds to do this computation? Actually, it's not even that bad. Negative times I squared is plus 6. So if I'm adding 6, I get 6 plus negative 2, 4. Are you guys checking this, I hope? 2 times, oh, but with a negative. Did I do this wrong? Negative 8? Guys?
7 plus 3i.
7 plus 3i.
How did you get 7? I'm getting 6, I'm getting negative 6 and a minus 2.
M is 7.
I mean 7 plus 3i.
7 plus 3i, great. Great, so negative 4.
4 is 4. It's negative 6 minus. So
Perfect. 4. Whew. Okay, and how about here? 7 times 2, 14, with a minus sign. 17 minus 14, plus 3i. So if that's r, here comes the magical calculation. What's its norm? 25. 3, 4, 5 is a Pythagorean triangle. We're all the way back to the first class. And 25 is strictly less than 15. Cool? You just did the Euclidean algorithm in the Gaussian integers. Now what?
So if you look at the C squared and define them,
Yes?
can you still define division? Like it might not be unique, but you still got to define division.
Awesome exercise.
Oh,
that is an exercise like 2 weeks from now. You can do it if you want to do it today, you can do it today. You will understand this much better if you do it today. That's exact. When you have z adjoin root -5, this direction is still scales 1. This direction scales root 5.
Okay. Or you can just say it kind of like the bases are like that.
The bases are, yeah, this basis vector is short and this basis vector is long. And it's so long that when you take one of these quotients, you might have a remainder that's no longer strictly smaller than the m that you started
And
with.
so that's why you said that it can't be
Yeah, it fails to be a Euclidean domain, and hence it fails to be a principal ideal domain, and hence it fails to be a unique factorization domain. Guys, don't listen to us. Ignore our conversation. We're going to have exactly this conversation like in 2 weeks. Yes, the geometry is crucial. Understanding the geometry of the Gaussian integer is crucial to understanding the algebra of being able to execute the Euclidean algorithm. Okay, so if you got something out of that, great. If not, we're moving on. Never mind. Okay? Can we continue the Euclidean algorithm with? So we started with. So what we know is that n is equal to mq plus r, where n was -2 plus 17i, m was 7 plus 3i, q came out to be 2i, and r came out to be 4 plus 3i. Let's continue the Euclidean algorithm. So this was a q1 and an r1. And now we try to write, and this was r0, and n was r-1. So now we're going to try to write next Karen, what's the next step in the Euclidean algorithm?
Do everything up and find that n.
We have to go all the way until the r hits 0. We have to go all the way, we have to continue this process until we have no remainder, until this fraction is a Gaussian integer.
So m equals to r1 times q plus r2.
R1 times Q2 plus R2. Okay? In other words, we're trying to find a Q2 near 7 plus 3i over 4 plus 3i. Go for it. Give me a thumbs up when you have the next iteration of this. You guys are never going to let me actually do what I planned to do, right? We're always going to go off on these very fun, very relevant tangents. It's a choose your own adventure course. I'm going to work on it while you work on it. Everybody's hard at work, right? Everybody knows what to do? Did you find, give me a hand if you found the next Q2 and R2. Okay, everybody's still working. Did everybody do this? Did I get these numbers right? Okay, continue. What is this near? 1? 37/25 is about 1. 9/25 is about 0.
So it's just one.
1.
Alright.
And if I set Q2 equal to 1, 7 plus 3i is 4 plus 3i plus times 1 plus 3. Because 3 plus 4 plus 3i is 7 plus 3i. Okay. The norm of 3 is 9, and 9 is less than 25. The norm of R2 is 9, and that's strictly less than 25, which was the norm of R1. Can we keep going? So now we're going to write Ming?
4 plus 3.
Yeah, let's use the variables and then put in what the, so what's the next equation?
Is that 1 2 Q3 plus
And it's exactly what you said, 4 plus 3i, which was R1, is equal to R2, which is 3, times Q3 plus R3. So what's Q3?
Is it 1 plus 1i?
And 1 plus 1i times 3 is 3 plus 3i, so R3 is equal to and once you get 1, it's pretty easy. So the last step,
Yes, get 0.
the last step you get 0. So R2 is equal to R3 Q4 plus R4. R2 was, where's R2? 3 is R2. This is R2. So 3 is equal to 1 times Q4 plus R4. Q4 is equal to
3.
Q4 is equal to 3, R4 is equal to 0. So this is the GCD, except if this had come out to I, like there are lots of choices that we could have made here. We didn't have to choose 1 plus I, we could have chosen some other nearby lattice point, which would have given us an error here. So that's why it's better to use ideals. The ideal generated by 1 is
All integers.
all Gaussian integers. And then the ideal generated by I is also all Gaussian integers. So it throws away this issue of units where we can't measure anymore. Charles?
If the remainder is 1, does that mean the next step, the remainder is always going to be 0?
Because the remainder is 1, in the next step you can just choose Q4 equal to R2 times 1, and the remainder is 0.
Because Q can be...
Q can just be R2,
yeah.
because R2 is a Gaussian integer. Q
Right.
needs to be a Gaussian integer. If this is 1, then it's just 1 times R2 with no remainder.
So if the remainder was I, it would still be.
If the remainder was I, you would do negative I times R2, which is still a Gaussian integer, with no remainder.
Does that mean as long as the remainder is a unit, it's co-prime?
Yes,
Okay, just like in the
exactly. So the way to measure coprimeness is that the ideal generated by two things is the entire ring. That's how you measure coprimeness now in this setting. Okay, we're out of time. Let me just give you one more exercise. Do the Euclidean algorithm, exactly what we just did, on two examples. 5 plus 3i and 2 minus 8i. And example 2, is 5 plus 3i. Same n, 2 plus 8i. And something fun will happen. So this is exercise 4, is it? 5? Exercise 5. Cool? Algebra in the Gaussian integers, the Euclidean algorithm in the Gaussian integers. I guess next time we'll prove that this actually works, that you will always find a remainder that's smaller. It's not hard to prove, but we'll think about it. And once we have that, then we do exactly the same process as we did in the integers, although now it really makes sense why we're using ideals. Or hopefully it's starting to make sense why we're using the language of ideals. Everything's going to work out nice. Have a nice weekend, and see you on Tuesday.